All right, so this is an example of a situation where for part of the motion, acceleration and velocity are anti-parallel, that is pointing in opposite directions. And so what I've done here is I've started the man out with an initial velocity of 4 meters per second. You can see that in the table here as well. Put him at time 0 at position minus 10, so that corresponds with this first row. And I've given him an acceleration of minus 0.5 meters per second. So initially, the velocity, his velocity is positive, but the acceleration is negative. So they're anti-parallel to each other. And you can see that from the table here, where his initial velocity at time 0 is 4, and then 1 second later it's 3.5. That's 4 minus 0.5, and then minusing 0.5 again, you get 3. Minusing 0.5 again, you get 2. And so it goes. We let him go for a total of 16 seconds, and you can see there's quite a lot of symmetry in the motion here. But let me initially, anyway, just run this so you can see what happens. So here we go. I'll take these two things away so he doesn't run into anything. So his velocity, you see the red is getting less and less and less. His position continues to increase. But then at velocity 0, he has a turning point. Now the acceleration and the velocity are both to the left, and he's speeding up. All right, so he speeds up during the first part of the motion when velocity and acceleration are anti-parallel. And then there's a turning point that occurs just about here. We can see it over in the data over here. We'll talk about that in a second. And then he starts then moving back from whence he came, and during that part of the motion, the velocity is negative and the acceleration is negative, and since they're pointing in the same direction, he speeds up on the return. So similar to the last one that we'd done, I have generated a motion diagram using these velocities and the average velocities. The same philosophy. So you're seeing the velocity start at 4 and increase by 0.4 meters per second every second, corresponding to this acceleration. And so during every second, I can compute an average velocity and use it to compute the displacement. And so since it's a 1 second time during this first time interval from 0 to 1, the average velocity is 3.75 meters per second, and therefore the displacement is 3.75 meters per second. And so these numbers, just like the last one we did, are all always equal to each other. And then the way we generate the x position is to, first of all, understand that he starts at minus 10. And then if he starts at minus 10 and over the first time interval he has a 3.75 meter per second displacement, then I add this number to that number to get that number. So this is his displacement at time 1, and then I take the displacement over the next second, 3.25, and add that displacement to his updated position to get his new position. And so it goes, and I get this. And if you look at the v column, when the velocity is 0, that's his turning point. This is going to turn out to be an important concept for us. And in fact, to motivate the next part of this, let's go to the chart part of this, and let me simply run this so you can actually see visually what's going on here. Okay. That was not right. Let's set it so it is right. So we're going to set him at, initialize it to minus 10, and start with a 4 meter per second velocity and set this to minus 0.5. That should do it. And now let's take a look and see what happens. You see, its velocity is steadily decreasing. It's got a negative slope, and now when the velocity passes the 0 point, he has his maximum displacement from his starting position. Okay, so when v is equal to 0, that's this row right here. Let me move this over here so you can see things a little bit better. He's as far away, his maximum displacement from his starting point is right there. And you can see it here, it's at 6, so it plateaus, and now his velocity, after that, his velocity becomes negative, and he does the mirror image of what he did coming back. And so you can see the symmetry there is here is his maximum displacement then, and he's just as far. His position here is the same as it was here, and his position here is the same as it is here, all symmetric about the turning point. And the acceleration is a little bit hard to see in this. Let me see if I can't increase that so you can read it a little bit better. Okay, minus 0.5. The scale isn't very good, but you can at least have some chance of reading it on that scale. All right, so let's do the same thing we did before and write the equations down. We'll do all of this in one thing here. Okay, so let's see, I want to change my color. And if I could just go over here and use this. So again, the equation for acceleration is just a acceleration is equal to a constant. And in this particular case, in our case, it's equal to minus 0.5 meters per second squared. The velocity is equal to the initial velocity, 4 meters per second, plus the acceleration times time. Let me write this in general form here. It's equal to, so in general, v is equal to v naught, the initial velocity, plus the acceleration times the time. So in our case, that's equal to 4 meters per second minus 0.5 t. And so this equation would generate all of these v numbers. If you put t equals 0 in there, you get 4. If you put t equal to 1 in there, you get 3.5. And then the position now, using the same argument we did before, it's equal to the initial position plus the average velocity, but the average velocity is equal to the initial velocity plus the velocity at time t, which is v naught plus at, divided by 2, that's the average velocity, times t. And so that's equal to x naught plus v naught t plus 1/2 a t squared. Same equation we did on the last one, but now let's make this particular to our example here. So this is minus 10 plus 4t. So this is in meters. This is in meters per second times seconds. And then plus 1/2 times minus 0.5 times t squared. Okay, so this minus 0.5 is in meters per second squared, and the time is in seconds, and so second squared is, of course, second squared is seconds to the exponent squared is second squared. So let's bring the calculator over here if I can, and let's just do a couple of points like we did on the last one. Okay, so for example, let's calculate the position when dragging this over here so you can see the time scale when t is equal to 8. Okay, so when t is equal to 8, this is minus 10 plus 4 times 8, putting 8 in for t, plus 1/2 times minus 1/2. Okay, so this is 1/2 times minus 1/2 times 8 squared. 6. Okay, so you can see that indeed the position is equal to 6. And so you can do the same kind of thing. We could do another one. Let's do t equals 12. If we do t equals 12 with this formula, we should end up with 2. And so that's easy to do with this little handy calculator. I can just copy this and paste it down here. And then I'm going to put 12 in instead of 8 for t here. And I'm going to put 12 in instead of 8 for t here. And I get 2, which agrees with that. So there you go. You have 2 examples, the last one we did and this one. This one, it will turn out to be similar to throwing an object up in the air. Similar thing happens when we do that, and so we'll talk about that separately.